Multiple masses. When dealing with multiple point masses, we find the potential and the field strength at a point by adding the individual effects. Let's look at an example where we're asked to calculate the gravitational field strength at point X, as shown in this diagram, where point X is 30 megameters from a line joining a 50 terakilogram mass, 40 megameters from this point, and a 30 terakilogram mass, also 40 megameters from this point. Well, straight away we can see that we need the distance between A and X here, and the distance between B and X. And this is 30 megameters and 40 megameters, so basically we have a 3, 4, 5 triangle, and this distance here will be 50 megameters. I'll also take this opportunity to label this angle as theta. Well, now I can find the gravitational field strength at point X due to mass A using this formula and putting in the values of the gravitational constant given on the data sheet. Terakilograms are 10 to the 12, so this is 50 times 10 to the 12 kilograms, and the megameters is 50 times 10 to the 6 meters, which we must square. This gives the gravitational field strength due to mass A at X of 1.3 times 10 to the minus 12 newtons per kilogram. We can now do the same thing for mass B, and now we have the smaller mass but the same distance, and this gives a value of 0.8 times 10 to the minus 12 newtons per kilogram. Gravitational field strength is a vector quantity, so we need to know the direction as well as the size of the field at X. The field due to A will be in the direction towards A, and the field due to B in the direction towards B. If I find the vertical and horizontal components of the fields at this point, I can from that work out the resultant. The vertical component of A is going to be up, and that of B will be down, so I need to take away the field due to B from that of A. They oppose each other. I can find the vertical components by multiplying the actual field strength found here and here by the sine of angle theta here. That's what I've done here. The vertical component of the gravitational field strength is the magnitude due to A multiplied by sine theta minus the magnitude due to B, also multiplied by sine theta. Sine theta is the opposite of 40 megameters over the hypotenuse of 50, which I've included here, giving a magnitude of 0.4 times 10 to the minus 12 newtons per kilogram. As mass A is larger than mass B, the overall field direction will be up. When finding the horizontal component, the field due to A will have a horizontal component to the right, and the field due to B will also have a horizontal component to the right, so now they add, and in this case I'll use the cosine of theta. So the horizontal component is that due to A multiplied by the cosine of theta plus that due to B multiplied by the cosine of theta. The cosine of theta being 30 megameters over 50 megameters, adjacent over hypotenuse. This gives a magnitude of 1.3 times 10 to the minus 12 newtons per kilogram, and this of course is now to the right. So now I can complete a vector diagram. Here's the vertical component upwards at 0.4 times 10 to the minus 12 newtons per kilogram. The horizontal component to the right, 1.3 times 10 to the minus 12 newtons per kilogram, and so the resultant goes from the start to the finish up here, and I'll label this as angle alpha. We can find the size of the resultant using Pythagoras, which I've done here, which gives a value of 1.4 times 10 to the minus 12 newtons per kilogram. The tangent of alpha is the opposite, 0.4 times 10 to the minus 12, over the adjacent, 1.3 times 10 to the minus 12, which gives alpha at 17.1 degrees. So we can write that the gravitational field strength has a magnitude of 1.4 times 10 to the minus 12 newtons per kilogram at an angle of 17.1 to the horizontal. Calculating the gravitational field strength at y is much simpler. As it lies on the line joining A and B, there is no horizontal component. A will be producing a field upwards and B producing a field downwards, so we simply need to subtract the value of the field from B from the value of the field from A. We use the same formula as before, but now we can just do one simple calculation. This is the mass of A minus the mass of B. This is the separation of y from A and also from B. This gives a value of 8.3 times 10 to the minus 13 newtons per kilogram. As A is a larger mass than B, the field will be upwards. As gravitational potential is a scalar quantity, it's quite simple to calculate the value at x and at y. We can use this formula. The potential at x is given by minus the gravitational constant multiplied by the mass divided by the separation. Putting in the values, this is the gravitational constant given in the formula sheet. This is the mass of A plus now the mass of B. They both add to the gravitational potential over the separation being the same from A and from B. Gives a value of minus 1.1 times 10 to the minus 4 joules per kilogram. Doing the same thing at y. Now we have a distance of 40 megameters and a potential of minus 1.3 times 10 to the minus 4 joules per kilogram.